to evaluate the given integrals. Okay, so evaluate. So let's say we are to evaluate number one, want to evaluate the integral of sine x divided by the square root of 1 plus cosine x. We're going to be using the U substitution method here. To get us started, let's go ahead and write down the formula that's going to govern our problem solving process. Okay, so the formula for U substitution is as follows. So you have the integral of a composite function f of g of x times the derivative of the inner function g prime of x dx. This can be rewritten using U substitution as the integral of f of u du. Think about this as a reversal of the chain rule. Okay, this happens where u is equal to the inner function g of x. The big advantage of the U substitution method is that it enables you to rewrite complicated integrals in a simpler format that enables easy integration. Okay, so let's take a look at how this works with this example right here. So we have to evaluate the integral of sine x divided by. Now, one thing to keep in mind is the way that you express your integral makes it very easy to carry out this U substitution process. Now, what I'm going to write this integral as is as the composite function times the derivative of the inner function. Okay, so I'm going to separate it. So we have the integral of the composite function, which is 1 over the square root of 1 plus cosine x. Is a composition of rational, radical, and a trig function. And then we have the other function, sine x. I'll put that to the side, sine x dx. Okay? Alright, the benefit of this is it makes it easy to identify what goes where. I will start with the inner function for my u, so we're going to have 1 plus cosine x be u, because that's the biggest function that I can select, that upon differentiation I end up with a multiple of the second function. Okay, so u is 1 plus cosine x. So we're going to go ahead and differentiate both sides with respect to x. So du dx is equal to the derivative of 1 is 0. The derivative of cosine is negative sine x. And now we want all the x's on the right and the u on the left, so multiply both sides by dx. So you have du is equal to negative sine x dx. Okay, you don't have to do this intermediate step. You can just jump from u to du equals negative sine x dx. Okay, this step is just to show you exactly what's going on. Alright, so now we know what du is. Du is negative sine x, and we have this other portion right here. So the question is, do we have a perfect match? If you look at what we have here, we have negative sine x, and over here we have sine x dx. Do we have a perfect match? The answer is no. We have a mismatch. What's the mismatch? The mismatch is that there's a negative with the u, and this function here does not have this function doesn't have a negative. So we have to rectify that difference before we can make a clean substitution. So to fix that problem, we're going to proceed to divide both sides by negative 1. Okay, so what's that going to give us? We're going to have the negative du. Let me fix my colors here. Negative du equals sine x dx. Now we have a perfect match. You see sine x dx matches perfectly with sine x dx here. Well, what does that mean? It tells us that we now have the freedom to replace this entire component right here with negative du. Okay, so always know exactly what's going where first before you carry out your U substitution so you don't make errors. Okay, so now we are now going to carry out the U substitution. This entire integral here becomes the integral of 1 over root u times negative du, which can be rewritten as you factor out the constant, which is negative 1 or just negative, integral of 1 over root u du. So this illustrates the power or the beauty of the U substitution method. This complicated integral has been rewritten as something really nice here. Okay? Alright, so what integration technique can we use for this? It's not that obvious, so we might have to rewrite this to make it doable. So how about we rewrite it using the properties of exponent as the integral of u to the negative 1/2 du. Okay, we have the negativity because we're reciprocating and we have 1/2 is just a rational exponent representation of square root. Now we can integrate using the power rule. Okay, so hopefully you remember what the power rule is. Let's just, yeah, so let's do it. We're going to apply the power rule here. So the integral of u to the 1/2 du is going to be applying the power rule u to the 1/2 plus 1 divided by 1/2, no, negative 1/2 plus 1 divided by negative 1/2 plus 1. Okay? So we're going to carry out the subtraction. Oh, let's not forget the c. So plus c. Okay, and then when we simplify, this becomes u to the negative 1/2 plus 1 is 1/2 divided by 1/2 plus c. Alright, so we have a compound fraction here. We can rewrite this. Just keep change flip or multiply the numerator by the reciprocal of the denominator. So we have 2 times, let's not forget the negative here. We have a negative here, and then we have a negative here. Okay, so we now have negative 2 times u raised to the 1/2 plus c. Okay, so are we done with the problem? The answer is no. One thing about U substitution is that, first of all, you carry out a substitution first, and then when you're done integrating, you resub. Okay, so here we did a substitution, sub, and then when you're done integrating, guess what? We're going to resub. What does that mean? We're going to resubstitute what we substituted out back for u. Alright, so our initial substitution was, we said let u be 1 plus cosine x. We have now integrated nicely. Now we're going to resubstitute what u is, which is 1 plus cosine x, back into the antiderivative or the integral. Alright, so negative 2 u to the 1/2 plus c becomes negative 2 times 1 plus cosine x raised to the 1/2 plus c. Okay, you can write this as in this format using rational exponents, or you can say negative 2 times the square root of 1 plus cosine x plus c. Alright, so whichever format you write it, that is correct. Ladies and gentlemen, this is the answer to question number 1 on how to use the U substitution integration method. Alright, so we have a question for you to consider. Now, when we had it set up as the integral of 1 over root u, how easy was it for you to evaluate this integral? Was it obvious that it should be rewritten as this, or were you thinking about another method to evaluate this integral? Let us know in the comment section below how complicated this particular step was for rewriting this integral as a rational exponent.